We're looking at the potato chip example in Chapter 10, example 1021, and I think it goes on to 1022. And we've got a manufacturer's decision here. So it's no longer just looking at null hypothesis. Do we have evidence to reject it or not? Is there evidence to the contrary, which is usually what the researcher is trying to prove, right? We usually have some effect, some difference that we're hoping is there. Well, no, in this case, the book makes a point of in acceptance sampling, or just tests as a decision. These are kind of equally important. We're still going to start out with, well, let's see. They're equally important. Let's see what the decisions are here. The decision is, here we go ahead and, we ship the chips if they're the appropriate saltiness. If they don't meet the standard, we're going to burn them. We will destroy the chips. Okay, so there's your decision. Statistics in action. And they don't have to be exactly. Number 68 in your homework is actually a little bit harsh. They say the decision is going to be if the sample mean is anything above 0, we're going to reject. And here's a hint to 68A. That's a 50% chance, right? You're centered on 0. Centered on 0, and this would be 50% of your curve. Well, that's not what we have here. This is 2 milligrams of salts, and we're not going to cut it down the middle. We're going to give it the old 95%. So 5% significance. Let's see, say alpha equals 0.05. So we've got a little tail over here, that's 2.5. We've got a little tail over here. We know this is a z-score. Why are we back to z-scores? I thought real tests use t-tests. Well, we have been told that sigma is 1. By the way, we've been told n is 50. We're going to sample 50 chips, test their saltiness. Might be a job I'd be interested in. And this is, so take 1 divided by square root of 50, it's something like that. Okay, and this is actually the standard deviation we're going to use. It's the sampling standard deviation, right? So these critical values, if this were a 0, this would be a negative 196, and this would be a 196. But we're going to turn those into real numbers. Let me erase those. This is going to be 2 plus, so this whoa, please undo that. This value is going to be 2 plus certain number of steps to the right. How many? 1.96. 1.96. What's this sampling standard deviation? Okay, and that gives us something like 0.03. It's just a little bit over 0.03. So this is 2.03. We got this. Oh, come on. And this would be 197. Okay, so what's the probability of a type 1 error? The probability of type 1 is alpha. So that's not too tough. And what does that mean? That means rejecting the truth or throwing out something that's good. We should ship these guys if this is the truth. Truth right here. However, there is a 5% chance that our sample lands over here or over here, and we're going to throw out perfectly good chips. So, you know, that's a cost, right? We don't want to throw away stuff that we've spent money and time making. And there's a 5% chance that we might do that. What is a type 2 error? I'm going to redraw this. Let me pause. Okay, so now we need an alternative situation. Right? This was, the top here was HO, and now our alternative, easy for me to say, alternative hypothesis is that the mu is not 2, but that's kind of hard to work with and hard to test or calculate anything. So through some judgment call, we think of a, maybe this needs to be further out here. We think of something beyond, over here in the rejection zone that would count as really unacceptable. We really don't want, if our average saltiness is 2.05 milligrams of salt per chip, then our customers are just going to hate us. They're just going to throw the bag away. So this becomes our new alternative mean. But we're going to use the same decision criteria. So this yellow is putting our test to the test. We're like, yeah, I see that, there's a good chance that we will, if it's 2.02, then the real mean could be 2. If it's 1.98, the real mean could be 2. So we're gonna use that as a decision rule. But what if our chips were really salty? How good is our test at rejecting things that we're supposed to reject? A type 2 error would be accepting something that's bad. So what's the probability of accepting something that we shouldn't accept? Let's take a look here. We still have the same value from above. So let's put this back in white. And that is the 2.03. This was cutting off the 5% tail, but we're going to bring this down, and this is still, 2.03, just on a different bell curve. And this is where we are going to accept a salty chip, right? This test, this is the test up here, where we're testing the null hypothesis, and we've set up this criteria. We'll accept anything that's below 2.03. Well, if the real mean is 2.05, we have all this area of accepting trash chips and shipping something we shouldn't be shipping. So this is the probability of a type 2 error. So if you need to review those, type 1 is throwing out what you shouldn't throw out, and type 2 is eating or selling what you should have thrown out. So 2 types of mistakes, right? I think we decided back here in type 1, this is a waste of money, waste of time and money. So that's your consequence. Over here, different consequence. We're going to sell the chips, but we're going to have some unhappy customers who then might stop buying our chips, and you decide which one's worse. Reminds me of the decision made in the movie Elf, where the guy's dad decides to ship the children's book so he doesn't lose money having to reprint it. But what's the consequence of shipping and selling a book that's missing pages? Yeah, I'll let you be the judge on that one. So now we need probability. How would we calculate this left tail? It's pretty sizable here. Well, we would use normal CDF, or you could calculate the z-score by hand and look it up on table A. CDF. What do we put in here? Let me pause it. So what numbers are we putting in our calculator? If this were just standardized, you would just use a lower bound and an upper bound. Our lower, of course, is basically negative infinity, and then 203. But it's not standardized. We have a mean of 205, our assumed alternative mean, and then remember we have the sampling standard deviation. It's not 1, it's 1 divided by square root of 50. And you plug that into your calculator, and that equals about 8%. 0.78. Okay, and I didn't draw this to scale. This is, should be, well, the yellow curve should be shifted a little bit to the right there. But we're just going to say that this area here is about 8%. If this is about 8%, then this is about 92%. This is, well, let's put this in yellow. This is 92. 92 too. Okay, this is the power of the test. And now let's put into words, what does the power mean? What's so great about it? Sounds like we want a powerful test, right? Well, a powerful, I guess you could argue that a significance, a strict level of significance is a careful test. But if you're too careful, then you're weak. So if we make this alpha, even further out to the right, we really cut into the power of our test. A powerful test is, the power of a test is the probability that we accurately detect an alternative mean. So, we start with this assumption, the mean is 2, but what if the mean really is higher? And that's what this 205 is. That was a what if. A hypothetical to our hypothetical. Now, we're not sure. Is it 204, 206, 2.10? We had to pick something. So this is an example of how sensitive this test is to picking up alternative means. So yes, there's a 95% chance we're going to accurately pick 2 when it's 2. So that's good, right? That significance tells us the probability of a type 1 error, and then the complement of that would be the probability of accurately predicting the null hypothesis. The power of the test is the ability or the probability to detect the alternative mean. Okay, I've said it a couple times there. So there you go. There's the 2 types of error. Make sure that you know that type 2 error is the complement of the power of the test. And then you should know what would give us more power. More power. Well, if you had less variation, right, then so there's one possibility that you would have all that as your power. Okay, so how do you reduce variation in sampling? You may get more specific with a subcategory of your population. You may have more precise ways of measuring. Another way is to, I guess I already alluded to it, just reduce the alpha. So this alpha was 0.05, which is split up into 2 tails here. So this is really 0.5 divided by 2. And I can't write up there, so I'll write it over here. Really 0.025. Well, let's make it 1. If you make it 1%, then you have, oh, I just said it the wrong way. I wish I could re-record this, but I can't. I'm in now. You raise the alpha. Yeah, the picture is helping me say the right thing. So not 5%, let's make it 10%. 10%, this is a 10. 10% will give us more power. It'll also make the probability of a type 1 error more likely. But if your type 1 error is not as costly as your type 2 error, you may choose an alpha of 0.10. Let's see. So I mentioned bring sigma down. Another way is to, of course, increase sample size. That also brings sigma down. We crank up alpha, not down, but up. Move that red line to the left. And finally, we could just, for our test, let's just try 2.06. Maybe there's a valid reason to move our alternative mean to the right. And so obviously if we had a curve of 2, even 2.10, then we're going to have a mighty powerful test, aren't we?